moved in constant time. So, okay. So let's take a look. Let's take a look at one particular. Okay, give me 1 second. Yeah, so, okay. Let me see. Can we connect this camera? No, there is no camera, right? Okay. Okay, so let's put it like this. Okay. How do we implement a double linked list? So first of all, recall, I guess, let's kind of step back a little bit and see why we need a double linked list. So we have header and footer in a free block. And then we said that, if you use an implicit list, the problem is that we would have to scan one block after another block after another block and so on. So it means we'll have to scan a lot of allocated blocks at the very least, and this is not good, because what's the point of checking the allocated block? It's not really available, right? But there is no choice because we have to scan the entire heap. So the way that we can solve it, we can create a linked list of free blocks. So anyway, the block is free, and therefore there is a free space, like previous and next pointer we can put right here. And if there is any space left, that's fine, right? So we can keep it. So what is the minimum block size if you have to use explicit lists? When we have header, footer, I mean, I guess footer we still need because I mean, for pre-blocks, even if you use this, I mean, it gives an advantage to scale lesson, but even if you get rid of footers optimization that I was talking about, that's only for allocated blocks. So footer we still need for a free block. So what's the advantage? So what is the minimum block here? So minimum, what is the minimum size? Okay, go ahead. Yes, yeah, 32 bytes, right? When we have a word size of 8 bytes. So, and it's already, so do we need to align? No, right? So because it's already aligned, right? So the size is already fine, right? So if you start, remember, if you have header is not aligned, then the payload previous next aligned, footer still aligned, right? Then header is not aligned, right? It's footer. So in header of the next block is not aligned, and again the payload and so on, right? So everything is fine, right? So as long as we have 32 bytes, at least we should be fine. So this is why I think the textbook also used 32 bytes. I don't recall whether the textbook was using 32 bytes. I think it was 16. Well, that was using probably 16 bytes, but that's because the word size is 4 there. But in the for implicit list, we don't need to put a previous and next pointer. But for the explicit list, we have to put previous and next pointer. So therefore, the minimum free block size that we can have is 32 bytes. If you have less than this, like when you split a block, you shouldn't be splitting the block, basically, right? So at least you have to have 32 bytes left. So that's one thing, right? So I guess even if we add one single linked list, that wouldn't help us because we would still have to align it. So we still have to put at least 16 bytes in the payload. So once we use at least 8 bytes, we have to, at least align it to 16 bytes. So therefore, we are not losing anything by keeping 2 pointers here. So now the question is, how do we implement a double linked list, right? So recall that your immediate neighbors, so some people I think are confusing this part, right? Because I've seen this question during office hours. So your immediate neighbors are still going to be your immediate neighbors. like header, footer. So when you are trying to do call listen, you're trying to call less with your immediate neighbors, not with the previous and next pointers. So previous and next doesn't mean that they're your immediate neighbors. They can be anywhere in the heap, right? And therefore, your goal is to make sure if you try to call less with this guy and you try to call less with this guy, right? So you want to check if there is a previous, if it's a free block, because previous and next pointer. So your first step would be to remove. So you want to remove that, right? So you want to remove it from the list. So for that, you have to have an operation which can remove an element no matter where it is in the list, right? So this is why we need a double linked list. So we have to have a constant time removal of the element no matter where it is in the list. So, and the same thing for this guy, right? So if it's free, we have to, the first thing that we do, we remove it from the list. So then we merge everything together. So let's say we were about to deallocate this block. So this block is about to become free, but it's not free yet. So we looked at our neighbors, we coalesced with them. While we are coalescing, we remove them from the list. So now the whole block becomes a new large block like this, right? Header and footer. And that's becoming your previous and next pointer, and you add it to the list. So don't try to optimize this part. So remove it from this from the list, remove that part from the list, merge everything together, and then add it again to the list. I mean, there might be temptation if it's this, let's kind of keep it in the list there, right? So something like this, but that's going to create more mistakes, right? So please remove everything from the list. Just use a simple procedure. Remove this, merge everything together, then add it to the list. Okay, so that means we have to have two operations: remove and add, right? So how do we implement remove? So I have a double linked list. So let's just forget that. I mean, this is a memory block. So by the way, how do you define previous and next pointer? So I just recommend to define a separate struct. So you can do something like struct node, something like this, right? It's up to you how you define it. Then you can have struct node previous, struct node next, right? Something like this. Again, it doesn't have to be the same name. It doesn't have to be the same points. It's up to you what you want to name it. And in fact, I'm pointing here to the node, which means I'm pointing to this area. So this area next points to this guy, right? To the payload area. This go points to the, like, I mean, if that was pointing to the immediate neighbor, right? So that would point to the payload area. You can choose to point to the header. It's up to you, right? So I just, I just kind of decide what area you want to. Do you want to point to the beginning, to the front of the header, or do you want to point to the payload area? Just decide it yourself, right? So, but I'm just giving an example where we have payload area. So then you can define struct like this. So whenever you reach the payload area in a free block, just use this, right? Struct, cast pointer to the struct. So now let's say we want to remove an element. So let's say we have a current element. And then we have previous element. And then we have a next element, right? Again, they don't have to be immediate neighbors, right? So let me remove these arrows to make sure you're not confused, right? So they don't have to be immediate neighbors. So you have this points to this points to this points to this, and this points to this, right? So again, it's up to you to choose where you're going to point, to the header, to the payload area, whatever you decide to do, whatever is reasonable, right? Just be consistent. So now we have current element that we are trying to remove. So how do we remove the current element? So there are two possibilities. So the current, so first of all, the current previous So remember that current has, I mean, I assume that current is the pointer to the payload, right? To the struct node, where we keep struct node. So we have current previous if it is not null, right? Because it can be null. So when is current previous is null? Okay, can you? Well, when it's the first element, right? Yeah, so if it's the first element, previous is null, right? So, well, unless you use a cyclic list, that's also possible. It's up to you, right? But let's assume it's just a regular list where the first element points to null, and then this last element next points to also null, right? Something like this, right? So we are trying to remove previous. So sorry, we are trying to remove. So we're trying to remove current. So current previous is not null. Then what? I go to current previous. So it's not null. Therefore it exists. So I go to current previous. So this points to some node. This node has previous and next pointers. So I have to update the next pointer. So next pointer should point to what? Next pointer should point to current next, right? So I want to update this, should become this, right? So I go to previous element, update its next pointer, and put it to the current next. So don't confuse this next and this next, and this previous and this previous, right? So don't confuse these two things, right? So maybe just for let's even name it differently, right? Just to make sure you're not confused. Let's call it predecessor and then successor. So therefore, you're gonna go current, previous, previous, next, right? You're gonna point to current next. Okay. So then, what else? So if it's previous is null, then what do I do? I guess I'm removing the very first element, so I need to update the first pointer, like pointer to the first element. So let's assume we have struct node first. So there is a first element, right? So make sure you initialize it in minute, right? Initialize minute, right? So don't initialize it statically, because if you initialize it statically, you may have some mistakes, like when there is a second trace file running. I think your static initialization will only be initialized once, whereas minute is continuously called, right? Whenever you call a new trace file. So don't initialize anything statically. Use minute. So don't put something like first equals to null as a global variable. You know, put first and then in minute put first equals to null. Okay, so we have this. So if so we want to update the first element. So else we want to update first, it should become what? It should become current next, because the current means its current was the previous first element. That means we have to make the next element as the first one. Right? So we updated the previous element. So the previous pointer. But now, so this guy now, sorry, the predecessor next points to this. But we also need to update successor pointer. So the successor should point to predecessor. So how do we do that? So we have a separate if statement after this. I don't know. Do you see if I write it here? Okay. If current next is not null, because current next can be null if it's the very last element. So if it's the very last element in the list, it can be null. So if current next is not null, then current next. Current next, so I go with current next here and update its previous pointer. It should be equal to what? It should be equal to current previous. Current previous. So basically predecessor, right? So it doesn't matter if current previous is null, that's fine. That means you are the that means this guy will become a new first. So well, wait a second. If this guy, give me 1 second. Current next. If can current previous be null? Well, yes. So current previous can be null, but we already updated the first element, right? So therefore, we will, if the current previous is null, we'll just record null, right? So that corner case is still counted. So we go to the previous, so we go to the next element, current next, which is successor. And successor has the previous field. So we update successor previous field to current previous. So that means the predecessor. Can everybody see this, the last line? Just let me know if you cannot see it. I can put it here. So does make sense? Yeah, I think I didn't miss anything, right? So I think that should be, so that's how removal will work. I mean, okay, go ahead.
If we have our nodes as structs, how do we know that like all of the memory is properly laid out?
What do you mean, properly laid out?
Like, how do you know that it's aligned if it's if you define it as a struct and then you just work with structs?
Well, you assume that the payload area doesn't change, right? So it still starts. I mean, look, this is just to, I mean, your node size doesn't change, right? You still have to use the correct procedure to calculate your node size, to align it properly and so on. So remember that your minimum block size is 32 bytes. That you have to guarantee. So whenever you allocate any block, you want to make sure that at least 32 bytes. Or whenever you split a block, you want to make sure that you at least have 32 bytes left, right? So if we cannot satisfy this condition, just make a block larger, right? So when you're splitting, right? So don't split it. So but assuming you have 32 bytes, you still have this alignment like you calculated previously, header and footer, you put it the way that you put it previously. Now you cast the payload area, pointer to this. There might be some space left after this, that doesn't matter. So you just cast the payload starting point to the struct node star, right? Does it make sense? So it basically placed in the payload area. So keep it as a separate struct because allocated blocks don't have that, only free blocks have it. So once you know that it's a free block, you can cast the payload area of the free block to this. And therefore you can get access to previous and next pointers. So yeah, so you have to cast struct node star, right? So yeah, so you have to cast whatever pointer payload struct node star. Okay, go ahead.
When I was implementing one, I basically did double reference instead of using a struct, but I'm actually using a struct to be cleaner. Does that matter when grading?
Yeah, so you just use the 2 pointers separately, right? Yeah, that's fine. Yeah, so you just in the payload you created previous and next, right? Separate pointers. Right? Yeah, so you just kind of incremented the pointer, then went to the next point. Okay. Well, as long as it's correct, right? So yeah, so yeah, make sure it's correct, right? So but yeah, it doesn't matter whether you put struct. I guess struct just a little bit cleaner, right? So but it's up to you, right? Don't put any requirements. Any other questions? Yeah, so it should be straightforward. So for adding, do we need to talk about adding, or the adding is clear? So removal, I think, is easier, like removal, maybe, but that's, I mean, removal is something that sometimes causes confusion, right? Because you have to update the pointers. But adding to the front, how would you add to the front? Okay, this is removal. Let's try to, how do we do adding? So let's say new element. I have current element. This is my current element. And then I have, should I call it new? I'm just kind of curious, right? So how do I call it? Let me call it N, right? So something like, oh no, just something like this, right? Yeah, so yeah, node probably is a bit unfortunate because we have struct node, but let me call it N. So I insert a new node to the front. So the next pointer points to current, and the previous of the current should point to this, right? But previously, so previously first was pointing to here, so now it has to point to here. So add is going to be what? So I will have to do a new previous now. That's obvious, right? Because that's going to be the first element. New next, not next is what?
First.
So that's going to be current, right? Well, yes, for first. Yes, so the first was previous value of the first, right? So and then we have to update first. So first previous should point to N, right? And then, but we have to be careful because first previous, what if I'm the first element? So again, we have two cases, right? What if I'm the very first element in the list? So there was no, first was null, right? So what if first was null? There was empty list. So no free blocks. So how would I do that? So I have to check. So this one is still fine, but I have to check if first is not null, right? Then first previous should be N, right? Let me put brackets so that you don't get confused. So then what? So then I updated first previous. I also need to update the first pointer. So the first pointer should become N, right? So first should now point to here. But before I update it first, I need to make sure that I updated the current node. So that's going to point the previous value of the first. So the first previous should now point to this guy. So this is node, but only if this node existed. If it didn't exist, then it didn't exist. So yeah, so and then node next should point to first, right? So that was, yeah, that was the previous value of the first. Node previous is now, right? So I think we have everything. Right? Okay, go ahead.
That reminds me that for removal, you need to have a case where it was the only free block instead of first equal.
Yeah, so if it's the only block, right? So okay, good point. Let's see if it's the first one, if it's the only block that I'm removing, right?
Like if it's the only free block left, and that's after removal.
Yeah, so let's see what will happen if it's the only block that I want to remove. So that is my current, and this is now, and this is now, right? Right, so block previous and next are now, right? So if I go here, previous is not now. No, that's not true. So else first becomes now, right? Then current next is not now. No, that's not true. So then it will just first is going to get now, right? So that's also covered, right? Yeah, so that's yeah, so you want to kind of write so that it's actually good to write algorithms where everything is kind of concise, right? So that all kind of corner cases are also covered. So that should be covered case. Yeah, but that's a good point. But that case is also covered. Okay, go ahead.
In my design, I keep the prolonging the fluent, so I don't have to present those conflicts.
Yeah, so if you have dummy nodes in the front and dummy node in the end, maybe maybe you don't need that. Yeah, so that's up to you, right? Okay, any other questions? Yeah, this is, I hope that you covered that at some point, right? I don't believe this. Yeah, so just to probably remind you of this stuff. Yeah, so. Yeah, it shouldn't be that hard, right? So just implement removal and add-on procedure. It's up to you whether you want to have a separate function or just do it in place, but probably you want to do separate at least for removal. Because that's going to be used multiple times, like for this neighbor, for that neighbor, right? And so probably you want to have a separate function for that. But again, it's up to you. Any questions? Let's see if it's yeah, I think it's visible here. Okay, so that hopefully will help you to implement an explicit list. So explicit list is not that complicated. Don't be scared. So you just need to maintain this double linked list, and that's it. And then it's it's even easier to scan this list. You just go from one node to another node, right? So you don't need to scan the entire heap. And what I heard previously that the food optimization that I mentioned, and plus the explicit list already supposedly give you 100 points, right? So is that true, right? Somebody tried that, right, already, right? So, but yeah, so yeah, I think that's what I heard, right? So therefore, I mean, I know that's explicit list was definitely not given 100 points alone, right? And segregated list would give more points than just explicit list typically, right? But it turns out, I think that you get already good savings from memory utilization from the so that I mean when I was employed, I implemented food optimization and segregated list, and that's still better than explicit list than food optimization because it still gives better performance and better problem memory utilization. But the benchmark that we use, it's probably the thresholds are kind of set a little bit lower, so therefore it will allow you I guess to get 100 points with explicit list and food optimization. Though I haven't fully verified that, but just letting you know, right? So you don't necessarily need to implement segregated list if you already done with explicit list and the food optimization. On the other hand, if you are confused maybe with the food optimization, how to implement that, maybe it's worthwhile to still explore how to implement segregated list so you can get more points. I think it will still give more points in that case. So just letting you know. I mean, ideally, I guess if you do like want to do something close. I mean, of course, what we are implementing is not the same as in libc, malloc, and free, because there's other challenges that they have to take care of aside from this, like for example, concurrency issues, and other things, right? But that, I mean, when we have something more kind of complicated, like segregated list and and food optimization, that's going to be probably closer to what real libraries have, right, for malloc and free. Not exactly, again, not exactly the same because there is a whole different level of complexity there. So aside from that. Okay. Just 1 second, let me open that. Okay, so let's get started. So I don't know if you will be able to cover all this algorithms today, but let's try to cover some of them. Oh, why is it disconnected? Okay, so today we will talk about page replacement. So, so far we covered, page tables, MMU, TLB, swap file, like swap files, swap devices. Yeah, so we still have something that we haven't covered yet, right? So so for example, we said, okay, how do we need to kick out some page from physical memory, but how do we do that? So how do we choose this victim page so that we can bring something from secondary storage? So yeah, so how do we solve that problem? So that's our main concern right now, right? So because this is something we haven't talked about, we just assume that there's some magic algorithm there, which will decide which page we have to kick out. So let's talk about this today. So this is also known as page replacement algorithms, right? So this is so the objective here is to minimize page faults. So remember that we had a case when we have a page fault, and then we realize, oh, this page is not in physical memory. I need to bring it from secondary storage, and so that I need to replace it. So, but how do we minimize the number of such page faults? How do we make it better? I mean, because we can randomly. So, what is the easiest approach? What is the easiest approach? By the way, not the worst actual approach in practice, but what's the easiest approach to kick out a page? Yes, yeah. So, and by the way, it's not the worst actually algorithm, right, in practice. But it will have its own issues. But yeah, we can also choose just randomly. Just say, okay, we'll kick out some page randomly and then just bring some other page. But we also want to see whether we can do better than this. So what we can do when we evaluate page fault rate is to evaluate algorithm based on some particular string of memory references, right? And then see how many page faults will happen in that string. So let's just assume we will have some string like we access page frame page frame or page number. That doesn't really matter here, right? So yeah, so we can say 1, 2, 3, and so on, right? So one thing to keep in mind that if the number of frames is really small, then the number of page faults will really be high, right? So this is also known as like thrashing, right? So when kind of a lot of time is spent to just bringing pages back and forth from secondary storage. So at that point, your performance degrades really a lot, right? So you have to really find some. I mean, it's really if you are really just have 1 megabyte of memory, but you have trying to kind of have virtual memory of several hundreds gigabytes, then probably it's not going to work well, right? So you're going to have a lot of page faults all the time, no matter what algorithm you're going to use. So this is all true for any algorithm, right? But at some point, once the number of frames is reasonable, the number of page faults also should become reasonable, right? And as long as you use some reasonable algorithms. So one thing that we can come up with, like the immediate algorithm that we can come up with, is first in, first out. FIFO, right? So we can have, let's say, a reference string 1, 2, 3, 4, 1, 2, 5. So that means some of these pages were already brought into memory, 1, 2, right? And 1, 2, 5, 1, 2, 3 again, 4, 5. So let's say the first case we have 3 frames. So that means 3 pages can be in memory at a time, right? So just for the sake of this example. So we bring a 1, 2, 3. So that's the first column, right? 1, 2, 3. Okay, then we realize, so what kind number of page faults we're going to get for 1, 2, 3? Well, because they were not in memory previously, we are already going to get 3 page faults. So we already have to count it, right? So for the initial page fault, we'll count it. So then we bring 4. So what is our approach? First in, first out. So what was the page first, right? So the first page was 1. So that should be kicked out first. So we kick out 1 and put 4. Okay, then it turns out that we read 1 again. So it seems like we did a mistake in our kind of calculation. We didn't do optimal way, right? Already we see that, right? Because we had just kicked out 1, and unfortunately it's the next page that we reference. So we have to kick out 2 now. So because that's the next one that is the oldest, right? So that's the oldest now. So we put 1. So now the oldest is 3. So we put 2. Again, unfortunately, algorithm is not optimal. We kicked out the page that is about to be referenced next. So we already have 6 page faults. So now we have a bring 5. So what is the oldest now? The oldest now is 4. So we kick out 4, and then we get 5. So what is the oldest now? 1, right? So we kick out 1 and bring 3. So then we kick out 2 and bring 4. So we have 9 page faults at this point. And now we are lucky, okay, 5 is finally in memory, so we don't kick out anything, so we just take it from memory. So there is first in, first out, right, algorithm. So let's see what will happen. So do you think, okay, let me ask this question. Do you think if I use this algorithm, I will, like increasing page frames will help me, the page frame numbers. So if I can hold for instead of 3, 4 frames, like, I mean, it seems like I have more space in memory, right? I should have less page faults, right? So naturally, I have more memory. I should expect better performance, right? That's kind of natural. So let's see what will happen. So we have 4 frames now. 1, 2, 3, 4. Okay, we get 1, 2, 3, 4 again, right? So then what do we do after this? Well, then we have reference 1, and that's fine, right? So let me see, 1, 2, 3, 4. 1, 2, 3, 4. Yeah, we reference 1, that's fine. And then we reference 2, that's fine. Yeah, so because, okay, 1, 2, 3, 4, that was 4 page faults initially, right? Then we reference 1 and 2. That is still fine because we have that in memory, right? Already. So that is fine. Then we have 5, right? So we kick out 1. Then we have 1, we kick out 2. Then we have 2, we kick out 3. Then we have 3, we kick out 4. So we have now what 8 page faults, right? Then we have 4 and 5, and that requires us to kick out. That requires us to kick out 5 and 1, right? Correspondingly, right? So because when we reference 4, there was no 4 was already kicked out previously, so we have to read it again. And when we kick out 4, we have to kick out, because we kicked out 5 and the next reference is 5 again, the same problem, right? We have to bring it. So now we have 10 page faults. So it's actually more than in the previous case. So we increase the number of frames. We have 4 page frames, but we have more page faults in total. So I can go through this example one more time, but you can see that it's one more page fault. So it means I'm having more memory, but it doesn't help me. It's actually making things worse. So this is what is known as Belitism anomaly, right? So this is when the algorithm actually gives you this more page faults than when you increase the number of physical frames. So certainly, ideally, we don't want to have that, right? So because I mean, you expect that that doesn't look reasonable, right? So I mean, you put instead of 16 gigabytes of RAM, you put like 32 gigabytes of RAM, and your performance goes down, right? So that's not what you expect. So okay, how much time we have? Okay. So again, we can look at this example when we have 7, right? So you can look how we can do 7, 0, 1 when we have free frames, right? Then we replace the first one with 2, then we 0 is referenced, nothing has to be replaced. Then we want to replace 3 because that's the second element. Again, 0, I think this is slightly shifted, but you can look it up. Like, I mean, this is kind of, I think 0 is kind of a little bit off here right on the picture, but yeah, so you can go through this example on your own, right? So you will see how many page faults we have in this case. Just as an exercise, right? So yeah, so you can, for example, measure number of page faults for different number of frames for the example, right, that we have looked at, and you can see that we can see this belated anomaly in this chart, right? So that it kind of goes up. So therefore, it's not something that ideally we want. We want to look for some better algorithm, hopefully, right, than FA23. So FA23 is easier, and in some sense it seems natural. That's means it's the first one, probably the oldest one. So why won't we kick out the oldest frame? Well, it turns out not the best algorithm. So let's see what the optimal algorithm is. Again, the problem with optimal algorithms is that even though they exist, they are not practical, right? So why, because why is that not practical? Typically because they rely on something that I need to know the future, and I don't know the future, right? So when I reference the page, I cannot predict what page will cause a page fault next, right? So I have to look at the program, and that's practically impossible. So the idea here is replace page that will not be used for longest period of time. So let's say we have 4 frames. So we have 1, 2, 3, 4 string, then 1, 2, 5, 1, 2, 3, 4, and 5, right? So let's actually go through this example. So we have 1, 2, 3, 4, 1, 2, 5, 1, 2, 3, 4, 5. So we have now 4 frames. So the idea is that replace the page that will not be used for longest period of time. So let's look at 1. So first we read 1, 2, 3, 4. That's fine, right? I am gonna read 1, 2, 3, 4. That's fine. That's the same way, right? I read them. I have 4 page faults already, right? Because it's the first access to these pages. So now I'm gonna say, okay, 1. So 1 is, 1 is doesn't cause any page fault because it's already here. What about 2? Yeah, it doesn't cause any page fault because it's already here. What about 5? So 5 now requires some replacement. So we have to replace some page. Which page will not be used the longest? Okay, go on. Yeah, so 4. So why is it 4? Because we can say, okay, if I replace here, so if I replace 1, that's going to be bad because it's going to be next, right? 2 is going to be also used right away, right? 3 also, right? But 4 seems to be the longest, right? So I'm going to replace 4. So now 4 is going to be replaced with 5. So now I have 5 page faults already, right? So then I have 1, 2, 3. That's good. There is no page faults for that. Then I have 4. Okay, so 4 now requires the page fault. Which of them is going to be the longest, right? Not going to be the longest period. Well, 5 is definitely not the option. I cannot kick it out. Well, I guess here at this point it's kind of a tie because there is nothing left, right? So I can just choose 1 and replace 1 with 4, right? So it's doesn't matter which one because they're kind of in the same position, right? You can just use some rule, just kick out the first one to break this tie. Yeah, so now we have 6 page faults. So I think it was the same string, right? So I just to double check that was the same string right here. Yeah. So here we have 6 page faults, and previously how many page faults we had? So let me see how many page faults we had previously. 9 page faults and 10 page faults. So definitely optimal algorithm did better, right? So this is much better. But again, it's not practical because I have to know the future. I have to know what will be the longest, the one that I will not use. But how do I know that? Unless I look at the I mean, I have to run the program to know that. So but it's optimal for a hit ratio, right? So and therefore we can compare whenever we compare any algorithm, even though that's itself is not useful maybe in practice, we can use this as a kind of baseline, right? So to compare against that and find something that gets closer to this. So what is the what can we do? How can we approximate the optimal algorithm? I mean, now it seems our goal to get somehow to the optimal algorithm, but at the same time, we don't want to be, we don't want to, when we get to the optimal algorithm, we don't want to, I mean, we want something practical that can be implemented in real hardware, right? And something that can be implemented in real hardware and software, and hopefully with some small overhead. So there is temporal locality, right? So we want to kind of recall that, right? So because we're going to the same page within a relatively small time duration. So given that, we can kind of approximate it. So it seems like it's global. I have to know the future, which will happen like, even like maybe after hours or days of running this program, right? But if I have temporal locality, I just need to kind of hopefully care about some small duration, right? So one heuristic that we can use is called least recently used. So evict the page that has not been accessed for the longest time. So instead of looking in the future, we are looking in the past and kind of trying to project the future based on the past, so to say, right? So this is what we are trying to do here. So of course, it's not it doesn't guarantee that looking at the past, we will get the same picture what we'll get in the future. It's quite possible that if I look that, I will see the entire different picture, but it's typically a good approximation. So now let's look at this example one more time. We have the same example. So we will have 1, 2, 3, 4 for least recently used. So that is the same because it's the first page fault that we have. So what element we're going to evict, right? So this is least recently used. So let me kind of put maybe number, some sequence number, right? Just for my purpose, right? 0, maybe 1, 2, 3. And then I'm accessing 1, right? Again, I'm accessing 1. So now 1 was used, right? So this is going to be 4. Right? So then I have 2, that's going to be 5. Then I have 5. Okay, 5 needs to be so 5 we need to kick out someone. So what we're going to kick out? Least recently used, the one that has 2 number, right? Because that's the smallest number. So I'm going to kick out this. This is going to be 5. So now 5 itself is going to be, let's put sequence number 6, right? Because that was just used. So then we have 1. So 1 is going to be now 7. 2 is going to be 8. Then we have 3. So 3, we need to kick out someone. So who is the least recently used? 4. So we're going to kick out this one. So that's going to be 3. 3 and the sequence number is going to be 9, right? So just, I mean, it doesn't have to be implemented that way, just for my convenience. I use the sequence number, right? Just when I draw this example. I mean, implementation can be, we will actually get to the implementation, how we can do that. So we have 5 and 3. Okay, 1, 2, then what? We have 4. Okay, 4. So what is the least recently used now? 5 is the least recently used. So that's going to be 4. Let me put 10. And then I have 5. You know, so 1, 2, 3, 4. And okay, least recently used now is this, right? So the 1 is the least recently used, right? So I'm gonna have this 5. So again, unfortunately, I've just kicked out 5. That was not optimal, perhaps, right? So, but now I'm gonna put 5 here. That's going to be 11, right? Sequence number, because that was the least recently used. So we have, yeah. So that's the result that we got, right? 5, 2, 4, 3, right? 5, 2, 4, 3. Yeah. So how many page faults we have? We have 3. We had 4 initial page faults, then 5, 6, 7, 8, right? 8 page faults. So let's compare it to 5, right? So what we had? 9 page faults and 10 page faults. So it's better than 5, but it's worse than optimal algorithm, right? At least better than 5 already. Does make sense? So just a question for you, right? Do you think that LRU will have this Belides anomaly or not? So what about optimal algorithm, right? So let's start with optimal. And will it have optimal Belides anomaly? No, right? So what about LRU? Yeah, it's also, yeah, so it turns out that what it's called, you know, so-called stack algorithms, right? You know, so if it can be shown that the set of pages in DRAM for n frames is always a subset of the set of pages that would be in DRAM with n+1 frames, if you can show that, right? If you can prove it, then it's a stack algorithm, right? You know, so you can the latest anomaly. I'm sorry. Like the stack algorithm. Yeah. So then it's a stack algorithm. So the latest anomaly will happen if and only if it's not a stack algorithm. So it turns out that LRU and optimal algorithms are stack algorithms. So that's an advantage of LRU, right? So at least you buy more memory, and you're not getting worse performance. As with FIFO, right? So that's clearly, even though it's not optimal algorithm, it still has that advantage. So if it's not stack algorithm, then it will have a Belides anomaly. If we can show that it's going to be a subset, like for n+1 frames, then we can prove that it's a stack algorithm. So you can try to do it yourself for optimal and LRU to prove that it's going to be a subset, but I'm just telling you that it's the case, right? Yeah, so how can we implement LRU? Well, you saw that I kind of had the sequence number, right? So, and had to kind of do some timestamps, right? So to say, right? So when I was accessing this time or maybe the other time, like when I was drawing this example, right? So you can implement this using so-called timestamps. So for example, you have physical page number, and then you update the timestamp, right? So hopefully like in the, so there is a couple maybe in the page table, I don't know, maybe you can put some different data structure. There is a way that you can do that, right? Yeah, so, and then based on this, you will have to decide which one to evict. So you have to choose the page for the lowest. So what does it mean? If I have to choose the page with the lowest, probably I'll have to scan the entire thing, right, to find the lowest one, right? Like I was looking at the, here and saying, okay, what is the lowest here? So how can we do that in terms of maintaining our? So by the way, let's actually talk. Since we have a little bit of time, let me kind of reorganize like we'll talk about the next algorithm next time, but let me actually go to the very end of the last slide and show you how we can potentially implement LRU, right? Before getting to the algorithm. So we have let's say what we can do, we can have a hash table. We can have a hash table and double linked list, right? So what so double linked list, so what is cache table for? Yeah, so but what are keys here, right? So the page number, right? Yeah, so yeah, I need some fast way to access page, right? So I need to maintain some data structure, which page to evict, right? And by the way, this is something that is implemented in file systems as an example, because LRU is not just for page replacement. There is something that you can use for cache in the file system. There's a different application of LRU, and this is just example from that, right? It's not how you implement it for LRU for page replacement in CPU, right? So it's just a different example. But that's nonetheless, the idea is the same. You have page number, or maybe you have block number in the file system, doesn't matter too much, right? Then how do you decide which of them to evict? So why do you need hash table? Well, you have a hash table so that you can access this page faster, right? So that you can say, okay, this page is such and such. I can go and hopefully with, you know, almost like constant time for allocate this page, right? Or the structure that is associated with that page, right? So we have a linked list, double linked list. So why is a double linked list? So why do we need double linked list? Well, I guess for the same purpose that we use it in malloc, right? So we want to remove it from that position, from the arbitrary position, right? We want to remove the element from the arbitrary position with the constant time. So there is an associated double linked list combined with the hash table. So you have a physical page number, you go here, you locate, okay, that's this element. Doesn't have to be the exact page, maybe there's some structure that represents that page, right? It doesn't have to be the page itself. So and then in that structure, you have previous and next pointer, which connects to a double linked list. So what will happen when you access that? You will go and remove that element right from here. So you remove. So again, this double linked list. This is why this is a constant removal. You remove it from this list, right? So this is the list, right? And you have to move it where? You have to move that to the most recently used part. So that means the head, right? Maybe it's a head or tail. It's up to you how you decide it. But I guess you put it to the head, most recently used. So in your tail, so now you have to maintain 2 pointers, head and tail. We didn't maintain head and tail for double linked list in the previous example, but you can have a tail as well, right? You can just update tail when you add an element, right? So it's also not going to change anything fundamentally. So it's the last element. So your tail is going to be least recently used. So and when you decide what to kick out, you go to your tail and kick out that element. So it's kind of combination of two data structures. The double linked list allows you to basically keep track what is most recently used and what is least recently used. So you put the most recently used block or page to the front. So and therefore your tail becomes least recently used. But you also need to access that fast, right? So you need to access an arbitrary page fast. So you have a hash table, which will have a direct pointer to that element in the list. So it's kind of a shortcut to that list so that you can find it in hopefully constant time or almost constant time. So now, of course, that's not practical for page replacement because even though it may be practical for file systems, to kind of cache blocks or some like or disk blocks. For pages, that would be what means I have to remove something from the list whenever I access some when I access some piece of memory, right? I have to remove something from the list, then insert it to another part of the. So that I have multiple memory accesses, right? That's not practical for CPU LRU implementation, right? So therefore, we will talk about some other approaches next time, right? So even though LRU is not optimal algorithm already, but even that not optimal algorithm, we cannot. I mean, we can implement it, but it's not going to be cheap. So we need to find some approximation of the optimal algorithm, right? So to say, right? Yeah. So that's what we're going to do next time.